Hello everyone and welcome to today's webinar on role of CFD in effective ventilation design during and post COVID-19. Our presenters for today are Aditya and Shada. Aditya is our CFD evangelist here at Simulation Hub. He deals with solving customer solutions and he provides solutions to our Simulation Hub app customers. He's also a technical blogger. Today, Aditya will take you through how HVAC plays such an important role in both controlling as well as spreading of airborne infection viruses. And he'll be also presenting you with some interesting ways in which we can improve our designs. Shadab here is our in-house CFD specialist. He has been working on creating and developing new CFD strategies for our Civilization Hub apps. Today, Shadab will take you through the two case studies that we are going to present. Through these case studies, you will get a detailed idea as to how CFD can be used to actually improve the design or to choose a better HVAC system and get the desired result. So before I hand over the mic to Aditya and Shadab, let me clear up some housekeeping items. So firstly, as you know, we are all working from home and there can be issue with the internet or something like that. So if in case you're not able to pick up a few of the slides or you miss out on the webinar at any point, don't worry, because we'll be providing you a recording of this webinar after the session. Also, a recording will be available on our webpage. And secondly, during the session, if you have any questions or you wish to ask the presenters about anything related to the webinar, you can post it directly in the chat box below. We will make sure that we'll answer all your questions in the question and answer session. So without any further ado, let me hand over the mic to Aditya. Aditya, over to you.
Thank you, Chaitanya, for the introduction. So, agenda of the today's webinar is like this. We will begin with a short introduction about COVID-19, its modes of transmission, and workplace preventive measures to mitigate the virus spread. Then we'll move on to the role of ventilation in building spaces and different techniques for assessing indoor air quality and ventilation effectiveness. We will also discuss how CFD can help in designing effective ventilation systems. And finally, we will show you two CFD case studies to demonstrate the role of CFD in analyzing and optimizing ventilation designs for during and post COVID-19 situations. We will end the webinar with a question and answer session at last. As we all know, this year 2020 started with unfortunate news of a new respiratory virus called SARS-CoV-2, and it's been 6 months since WHO declared public health emergency of international concern. Most of the offices, schools, colleges are shut off, and for those it is possible, are working from home. Some are trying to reopen businesses partially to keep them running, and are looking for guidelines to create healthier and risk-free work environment for their employees and customers. On the other hand, this pandemic is creating enormous pressure on our healthcare infrastructure. Our healthcare workers are working overtime by putting their life at risk, and protecting their health is going to be a primary concern for us. Such a crisis calls for innovative solutions that will help us adapt to current situation and in time restore our normal lives. So we'll first understand the mechanism of virus transmission. From the studies, it has been observed that the virus SARS-CoV-2 resides in a respiratory tract and mucous membrane of infected person, and it is emitted from a droplet exhaled by a person while sneezing, coughing, talking, singing, or any activity in which he or she exhales air. Initially, it was considered that virus can only be transmitted through larger droplets, which falls on the ground within a 1 to 2 meter of distance due to gravity, and considered as a fugitive transmissive disease. But now WHO has revealed that SARS-CoV-2 may also spread through the airborne transmission, from smaller droplets to aerosols. These aerosols have a capability to remain airborne for a longer period of time and can travel through significant distances by the air currents. Other organizations that deal with building environment control systems, such as the REVA and ESHRE, also acknowledged the potential airborne hazard indoors and recommended ventilation strategies accordingly. So, here on screen, you can see the hierarchy of controls suggested by US Center for Disease Control and Prevention in mitigating COVID-19 hazard at workplace. As you can see in the figure, the most effective and ideal way is elimination of virus. Like if there is a no infected person entering the building, there will not be any chance of infection spread. But it comes to know that many infected people are asymptomatic in nature, and it is difficult to identify them. So the next most effective way is engineering controls. And this is the focus of today's webinar. And as you go down, you can see the least effective measures like protecting individual with PP and administrative controls, as these are mostly dependent on people. In engineering controls, ventilation and air distribution is a primary control strategies to avoid spread of airborne contaminants from one person to another, sharing the same space. This is achieved by the dilution of air contaminants around the source and removal of infectious agents. Other techniques are filtration, that is use of high efficiency HEPA filters, disinfecting air with UV light and bipolar ionization, and controlling humidity and temperature levels. But in this webinar, we will be focusing more on ventilation and air distribution strategies only. So we'll see the role of ventilation in building spaces. There are four major roles of ventilation in indoor environments. The first one is to maintain good indoor air quality with contaminant concentration below acceptable level. The second role is provide sufficient quantity of fresh air to maintain required oxygen levels and healthy environment. Third one is distribution of this good quality of conditioned air throughout the room effectively. And finally, in some critical applications, ventilation used to create pressurization to avoid contaminants entering the room or to avoid spread of infection from the room. Let's see each point one by one. Indoor air quality is defined as quality of air inside a building as represented by concentration of air contaminants and thermal conditions that affect our health and comfort. Controlling common indoor pollutants like dust particles, bioaerosols, various gases like carbon dioxide, and harmful gases like carbon monoxides, VOCs, radon, ozone can help reduce the risk of indoor health concerns. While some of them can be filtered out using high efficiency HEPA filters, the other gases like CO2 need to be exhausted and replaced or mixed with quantity of fresh air before being filtered out and supplied into space. As there are some standards like air change rate like ASHRAE 62.1 ventilation for acceptable indoor air quality that provides guideline on air change rate per hour required for the different applications like hospitals, kitchens, labs, colleges, banks, etc. As you can see in the table, this quantity of air is distributed in the space using various techniques. The most commonly used ventilation system in offices is overhead ventilation system that mostly works on the principle of mixing ventilation. In this system, the conditioned air is supplied from ceiling, mixes with existing room air, and exits the space through the return grill placed in the ceiling. But for larger and taller buildings like airports, shopping malls, displacement ventilation strategy is used. Here, the conditioned air is supplied in a low velocity at a lower height directly in the occupant zone. This air is then displaces the existing hot air and exits the room through the ceiling grills, taking the advantage of buoyancy. The next ventilation strategy is underfloor air distribution system, which is designed to take advantage of both mixing as well as displacement ventilation. Conditioned air is supplied here from underfloor plenum and existing air is exhausted from the top. The unidirectional flow is maintained here. As a recent development in ventilation strategy, many researchers have suggested the use of personalized ventilation systems after the outbreak of SARS 2003 and MERS 2012. This ventilation strategy is designed to focus on air quality provided to each occupant at his inhalation zone and facilitates each occupant to control air parameters individually. Personalized ventilation systems, if provided with local exhaust source control, may offer protection against exposure to contaminated air and can be effective against airborne transmission diseases. The next role is pressurization. In some critical applications, pressurization is used to avoid leakage of contaminants between adjacent spaces. Likewise, here in airborne infectious isolation room, where negative pressure is maintained to avoid escape of infectious particles from the room, and in operation theaters, where safety of immune compromised patients is handled by maintaining positive pressure to avoid infiltration of outside contaminated air in the room. This application is also found in some clean room applications from pharmaceuticals and electronic industry. So till now, we have discussed the role of ventilation systems in maintaining air quality and keeping contaminant concentration low. Now we will see the impact of poor ventilation design and how it could be fatal. To explain this, I have two interesting real-life incidences studied by researchers around the world. One is from call center in South Korea, where 97 people got infected from SARS-CoV-2, from which 94 are working on the same floor. As seen from the study, this could be caused due to the overcrowding of occupants in the space and poor recirculation of centralized ventilation systems. The another famous incident is from Guangzhou restaurant in China, where the infection was transmitted among 10 diners from 3 different families. As you can see here on screen, the person colored violet was the only known source of infection, and infected people shown in red. Here, infection was transmitted beyond a distance of 5 meters. That is social distancing guidelines provided by WHO. The author has concluded that this could have happened due to the poor directionality and strong air currents of HVAC system, as you can see here in CFD study. So, before finalizing any HVAC system design, it is always preferable to know the airflow pattern and contaminant removal efficiency. So, before finalizing HVAC systems, it is always preferable to know the airflow pattern and contaminant removal efficiency. So, in the next slides, we will see the different techniques of assessing indoor air quality and ventilation effectiveness. First, we will see the different theoretical concepts for assessing ventilation effectiveness. Mean age of air. Mean age of air is the average time that air has spent in a zone of building accumulating contaminants, and it is an important factor in assessing quality of ventilation. Air change rate per hour, popularly known as ACH, is a measure of how many times the air in a room is replaced in a duration of 1 hour. The next one is air change efficiency, is a measure of how quickly air in a room is being replaced. And the last one is a contamination removal effectiveness, is a measure of how quickly and effectively an airborne contaminant is removed from the room. To calculate air change efficiency and contaminant removal effectiveness, we need few parameters. In next slides, we will see how to extract these parameters using physical measurement techniques. In this slide, the first image on the left shows person setting equipment to perform tracer gas ticket testing. That is, first fill the room with amount of tracer gas and run the system and check how much time it takes to reduce concentration of tracer gas below the accepted level in a different parts of room. Another image is showing evaluation of flow behavioral pattern of tracer gas SF6 in designing exhaust strategy for airborne infection isolation room. And on the right, you can see some sensors and devices which can measure the concentration of various contaminants in air, like VOCs, CO2, carbon monoxides, PM2.5 particulate matters. And it is also useful in checking temperature and humidity levels. Also, IOQ can be assessed using advanced numerical techniques like computational fluid dynamics or CFD. CFD uses various numerical methods and computational algorithms to solve governing equations like mass, momentum, and energy to evaluate flow behavior for given HVAC designs. CFD comes with different approaches like discrete particle modeling for larger and heavier particulate contaminants and species transport for aerosol and gaseous contaminants. CFD simulation results provide quantitative data like contaminant removal effectiveness and qualitative data like contour plots, flow lines, and tracer gas particulates to predict the contaminant concentration and its actual flow path inside occupant zone. In comparison with CFD and physical measurement techniques enable us to evaluate things on the real setup, and it can be possible after construction and installation of system. On the contrary, CFD can be done at design stage itself. Physical measurements are only possible at a limited probe locations, where in CFD, entire volume can be assessed with detailed flow insights. What if scenarios are very hard and sometimes impossible to evaluate physical techniques. Whereas in CFD, any design configuration can be simulated, and that helps in taking design decisions at a very early stage of design cycle. But CFD expertise is required to run simulation along with software installation, licensing cost, and computational resources. So traditional CFD simulation process goes like this. It starts with geometry of building space in any CAD format, like a beam model. We need to extract fluid volume from geometry and then discretize it into small cells to perform numerical operations. Then we solve different governing equations in these cells, and finally we extract results from different post-processing techniques, like here we have shown contaminant concentration inside an office space. As you see, this requires lot of CFD expertise and manual interventions. And if you are interested to see results for different configurations, then the whole process has to be repeated, and which consumes lot of time. So what if there is an alternate solution that could automate all CFD processes and autonomously run the simulation on cloud? And that is where we came into picture. In simulation of CFD, our vision is to transform human life by the democratization of technology. And technology here is cloud-based upfront CFD. The CFD apps not only for just CFD engineers but also industrial designers. Here in this context, HVAC designers or building architects. They themselves should be able to use this app and CFD to evaluate their designs. Using the Simulation Hub CFD platform, we have developed the Autonomous HVAC CFD app, an app to evaluate occupant thermal comfort parameters like PMV, that is predictive mean vote, and PPD, that is percentage people dissatisfied. The technology preview of the app is already released and available for you to experience. We are also working on including IQ parameters like contaminant concentration and CRE. The app works on OpenFOAM solver technology in a backend and runs CFD simulation on the AWS cloud platform. And so point to note here is this app runs on a cloud. That is, you don't need any high performance computational resources to run CFD simulations. You only need good internet connection and any device from which you can access it. The app workflow is pretty simple. First, you need to upload the building design model in any supported format like Revit or Step. Then you will have to create multiple design configurations, that is to try different air distribution systems with diffuser types, location, and select multiple scenarios on the basis of heat load and external weather conditions. And with one click, you can run all the CFD simulations of all possible combinations. And as the whole process runs on a cloud parallelly, it requires not more than few hours. After completion of simulation, you get CFD results compiled in a technical report that could be directly submitted to end client. So from now, I will hand over to my colleague Shadab, and he will take you through the two case studies developed by our CFD team. So Shadab, over to you.
Thank you, Aditya. And hello, everyone. So now I'm going to present the two CFD case studies to show how CFD can help in designing the ventilation system and how to analyze the CFD results to design your better system. So for this purpose, we are starting with the first case study, that is airborne infection isolation room ventilation design. As we all know that currently many countries in the world are in community spread stage. Lakhs of people getting infected and thousands of people admitted to the hospital in critical condition. So there is a high demand of isolation rooms. So to fulfill this gap, many people are going for easily to install, assemble and portable isolation rooms that is based on containers and etc. But still ensuring the safety of a frontline health worker and evaluating the ventilation efficiency is a bigger challenge. So now, before directly going into the CFD problem, let's have a look. So let's have a look into the typical construction of isolation room. So here on right hand side you can see isolation room contain anteroom, patient room and attached with the bathroom. As this isolation room is designed to control the airborne infection, so it has to maintain the negative pressure which avoids the leakage of air from inside to the outside. Although there are some guidelines and strategies are provided by many organizations and institute. So those are like this. You have to maintain the negative pressure and pressure and at least pressure differential of 2.5, and you have to maintain the ACH more than 12, and this followed by all over the world. And the use of HEPA filter is best before the supply unit and after the exhaust unit, and it is best practice to discard the exhaust air directly into the atmosphere. But here the major question still remains the same: how you can design the effective airflow pattern. That itself depend on the position of supply diffuser and outlets that govern the contaminant distribution. So now coming back to our case study, the objective of the study here is to optimize the location of supply diffuser and exhaust position to form the effective flow inside the system that remove the contaminant from the space as early as possible without allowing to spread. So for this problem, for this case study, following inputs are considered. This is the isolation room, and 12 ACH inlet supply flow rate is maintained, and the suction flow rate is of exhaust is 10% more than the supply to maintain the negative pressure system, and a pressure differential of 7.5 is maintained, which are aligned with the ASHRAE standards. Here mannequin is the only contaminant and heat producing source in the domain. Now coming to scenario case stages. Here we are considering 3 different configuration in which we have changed the outlet position and the bed position. In all 3 cases, the supply of inlet is fixed, and only in first case the exhaust is placed near the bottom and it is very far away from the bed, and in second case the exhaust is placed exactly on the top of bed of mannequin, and third case the exhaust is placed adjacent to the mannequin. As I said, here mannequin patient is the contaminant producing source in the domain. So let's model how the contaminant is entering in the domain. So cuffing process is the cause of contamination, so which is a short-term and transient process. And you can see on the right hand side top figure, it is an ideal characteristic curve of a cuffing process which obtained by Gupta et al. Through in his experimental work, which is similar to like skew triangular pulse, and this is only for duration of cuff. For simplification, in our CFD case study, we have modeled the characteristic curve as shown in figure 2 with mass fraction of pathogen gas 0.02 is entering with the cuff gas in the room. Now, in this slide, I summarize the CFD setup that we have chosen for this study. I already know that many people are not from the CFD background, so I won't go much detail in it. But so, as we all know that ventilation flows are bouncy driven and turbulence in nature. So we need to solve the governing equations of continuity, momentum, and energy equations. Apart from that, we also need to solve another governing equation to give the contaminant and spread and residence time in the space. So here, as our contaminants are airborne, which are like tiny microparticles that only carried by the air flow currents. So for these assumptions, we have modeled this physics by using the passive scalar transport equation. So in addition to 3 governing equations, we solve this equation as well. Just to give you more information about the simulation, we perform the simulation in 2 stages. In the first stage, we perform the steady state simulation to obtain the flow pattern in the room. And then on the same setup, we started the transient simulation of time, including the cuffing time, and plus some extra time is provided to see how the contaminant is distributing and removing from the space in different scenarios. So let's get back to the results analysis. So first we are analyzing the case of a ceiling supply and the bottom exhaust. So you can clearly see in the steady state flow line that cold air is directly hitting the air, then it is recirculating in the room. It is a big recirculation though, and finally leaving from here. So let's see this recirculation pattern, how it governs the contaminant distribution. So you can see over here a large chunk of concentration, contaminant concentration, is emitting into the domain, and initially it is moving into the top upward direction. This is due to the inertia associated with it. Once it lost the all inertia momentum, then it spread in the room and finally leaves from the here. Let's say analyze the second case, which is a ceiling supply and a top outlet. So you can see that near the bed, near the exhaust, all currents are in upward direction. And you have to note that mannequin is also creating the plume effect that is due to the natural convection. So the all currents near the exhaust in upward direction. So let's analyze the contamination behavior in this case. So as I said, initially the contaminants is moving again in the upward direction, and from the upward direction it is directly leaving, and it is leaving the space. So this is this system is near to our ideal system, we can say, because the another objective of the isolation room is to remove the contaminant from the on-site itself. It does not allow it to spread. So this model, this flow behavior, it does not allow it to spread in the room. Now let's analyze our last case 3, that is the ceiling supply and the bedside exhaust. So here still you see the same recirculation behavior on the mannequin head. Now see the contamination behavior in this case. Again, initially the concentration contaminated gas moves upward direction, but slowly it spread in the room and finally leaving from here. So finally leaving from here with this convective currents. While comparing the case 3, this design 3 with the design 1, the difference is that the time required for the contaminants to leave the room in design 3 is less, while in design 1 it is very high. So all these results, what we are saying, it is in qualitative form. Now let's analyze the results more detail in quantitative form. So you can see on right hand side, it is a maximum concentration of contaminant gas in the room and how it is decreasing. So from here, you can see that during the coughing period, that is up to 0.5 seconds, the concentration of contaminants in the room is constant, that is equals to 0.02, that what we are applying. And after that it start decreasing, and then depending on the different case flow patterns, each model, each design have their different behavior. So from this graph, we can infer that ceiling supply and top exhaust is performing very well, because near the exhaust, all currents are in upward direction. So the contaminant is leaving the room without spreading. Whereas you can see in design 1, that is the ceiling supply and bottom exhaust, there is a large recirculation done, and there is a giving high time for the spreading, and after that contaminants also leaving the room very slowly. So from this graph we can say over here that our ceiling outlet and top exhaust model is good design and is performing well and compared to other designs. Now I will show you another CFD case study of a new isolation room. You can call it as a new generation isolation room based on containers. So this is a container, and this is the fluid volume or a patient room, you can say, and this is the supply position, exhaust position. Here we are not performing detailed study. I'm just showing one flow velocity contour overlap with the velocity vectors. To show here, one important thing is that to maintain the 12 ACH, it may happen you can get like heavy high velocity on the mannequin, and due to the this, there is a draft high draft temperature. It's like high draft is occur and the thermal comfort problem may arise. So this is like typical example. Here also you can use the same CFD setup and analyze the each and everything in detail. So not going in detail, moving ahead, let's summarize our case study 1. As we have seen that if we use our CFD effectively, we can design the effective ventilation system that definitely provide us high level of safety to the health workers who is risking their life daily to save us. And coming back to our standard isolation results, we conclude that our top ceiling supply and top exhaust model is very good design and it is performing better. And I would like to add over here that these results are only applicable to the inputs what we have considered. And one more thing is that CFD is highly dependent on the physical space and presence of any objects or the diffuser type itself. So every time you need to perform the CFD simulation to get the key insights. So in a way, a HVAC designer can use the CFD to evaluate his design and perform the design cycle very fastly and make his design better. So now moving ahead with case 2, it is related to office space ventilation design. As my friend already explained, what are the chances of transmission in office spaces with the example of South Korea call center. Now coming to problem statement, Here the objective of problem is to show the effect of different ventilation system on the airflow pattern, and assess the indoor air quality, and finally estimate the contaminant removal efficiency of each HVAC system. So for this purpose, we have considered our office space of CC Tech at Pune. Our office is operating in a low capacity. Adjacent seats are always empty beside the mannequin. It is following the social distancing norm, you can say. And here supplying flow rate is 6 HCH. And the total mannequin in the zone is 30, out of which 6 are the infected contaminant mannequins which release the contaminants in the room. One more thing we need to note here, that here the 30 mannequins are the heat producing elements, and 60 CPUs are as well. Here the CPUs are more because some other people are working from the home because of this corona pandemic. Now let's move to the comparing design options. Initially, we will first perform the CFD results of overhead diffuser with underfloor diffuser. And I already said the 6 mannequins are infected one. So we model the contaminant released by each mannequin with respect to Cow et al. We exhale 1 liter per minute contaminant air containing a mass fraction of 0.04 pathogens into the room continuously. Now let's summarize the CFD model. This is very similar to the CFD setup what we have considered for the isolation room. Only difference is that here it is a complete steady state simulation. In addition to that, we also perform the calculation of local mean edge of air to assess the stagnant zone or any dead zone in the design. So first we will compare the results of we are performing the one-on-one comparison between the overhead diffuser with underfloor diffuser. On the top, these are the contours of velocity and concentration taken at the human nose level, and similarly for the underfloor diffuser as well. Let's analyze these results in more detail. You can see over here, there are the sum of so you can see over here, this is the high velocity region near the diffusers. This is due to the draft producing by the diffuser. So this draft also may create the thermal comfort problem for the mannequins. Let's see how the velocity distribution in the UFAD case. Here you can see the velocity distribution mostly uniform, and it is in good range of 0.1, which is a comfortable range. Now let's see how the contaminant concentration at the same level for the overhead diffuser. You can see the average contaminant concentration in the overall space is falling between 40 to 60. And one more thing, you can see how the contaminant is spreading due to the flow current and the region of high contaminant concentration. One major thing I want to point out over here, that this is a dead zone. So dead zone contains the high concentration of contaminant. So there is a high chances of getting infected there. So we need to increase the ACH if we need to control the airborne infection. So now let's analyze the UFAD results, which is very good. You can see the contaminant concentration is below the 20 ppm. In overall sense, it is performing well. Still, there is some problem in the dead zone. So we need to provide extra diffuser or need to do some extra thing for this one. Now, let's analyze the flow pattern of each diffuser in detail. You can see over here, this overhead diffuser, it is a CAV square plug diffuser. So you can clearly observe the Konda effect. Actually, it is very essential and it is very required for achieving the good thermal comfort, but this is not recommended when airborne infection type of contaminant is present. So we need to avoid the mixing type ventilation system. to control the airborne infection. And similarly here in underfloor, you can see the swirl effect produced by the UFAD system. And these are the some zoom image on the right hand side. Now let's analyze the system which has a mean edge of air more than 5 minutes per second. So in square plug diffuser, you can see this is the iso volume contour. So these are the region. So these are the region who have the mean residence time for the 5 minutes second, which emphasizes that this area has a low air change rate, or it may have the stagnant zone. As we already seen here, this is a stagnant zone. So that's why in iso volume you cannot see here. While comparing the underfloor diffusion, you won't see any much iso volume in the human occupied level. So with that, we can conclude UFAD is performing better in all cells. It is giving the uniform mixing and removing the contaminants from the space, because UFAD system has this nature that it creates the localized mixing and it is overall displacement. So it always elevates the contaminant from the human occupied zone to the upper level because of the buoyancy effect. So UFAD system is a good system compared to overhead system to control the airborne infection isolation. So here another one question arises. So what if I already have the installed overhead system? So what should I do? Should I replace my system? Because installing capital cost of an HVAC system is very big. So there's also all of a sudden replacing the overhead system because of this pandemic is a big problem. So to address this problem, we also perform another simulation containing the portable purifier, placing on each table, containing efficiency of 99.7, which is equal to HEPA filter, and having the suction flow rate of 24 CFM. Now let's analyze the results in detail. So you can see this is the bottom. This is the overhead diffuser plus purifier results. So you can see the velocity contour is more or less same. Only difference is that you can see the some of the high concentrated spots. So this is due to the this plane is very near to the exhaust, so that's why you have seen this one. Now let's analyze how the purifier solve our problem. So we can see over here now the contaminant concentration is very low and it is very identically equal to the UFAD system. In some sense you can say it is giving better than UFAD as well, because UFAD is sucking this purifier is sucking the air from the local zone and purifying. So we can say like in the vicinity of a mannequin, there is a pure contaminant free air will be there. Now let's analyze the flow pattern again. So you can see this time the square plug diffuser does not have any bigger conda effect like before, because this purifier sucking the air locally, so it is creating mixing locally. So now similarly analyze the streamlines in zoom. So this is a streamline. Another one thing over here, this is the glyph plot, which represent that how the air is entering from the side and the purified air is again leaving back into the room. So in this way you achieve the localized uniform mixing. Now let's analyze the is this using the purifier solve our residence time or dead zone problem. So we can see clearly that in this case we have no as such volume which has a more than residence time of 5 minutes. So with that, so we can say like, but if we use overhead diffuser along with purifier, it can solve our contamination problem and it will improve the air quality inside the office space. So now let's summarize our case study. After observing all our contours, streamlines, and mean edge of air distribution, we can say that overhead diffuser is less compared to UFAD system in terms of performance. So overall UFAD system is good design. If you have already installed overhead diffuser system, so it is better and it is always advisable to go with purifier to control the airborne infection isolation room. In this way, we can design the effective ventilation system in office spaces, and we can reduce the high risk of transmission in office space. Again, I want to point out that this results is limited to the input what we have considered. And with this, I have completed all my things. Now I will hand over this session to Chaitanya.
Okay, yeah, thank you, Shadab. It was a very knowledgeable session, and I think our viewers also got a very good idea about how we can effectively design the HVAC system. Now we can start with the question and answer sessions, and we already have a few questions asked by our participants. So I'll ask them one by one. So Shadab, we have a question that which turbulent model is used for the fluid flow in discrete particle simulations?
Okay. Yeah. In our studies, we have considered the K omega SST turbulence model, which is a two equation model from the RNS family. It can capture the complete physics from near wall effect to complete turbulent flow. That's why we have used this solver. We have used this turbulence model.
Okay, yeah, thank you. Okay, so we have another interesting question. So I think this is more about particles with mass. So microplastic pollution is an unknown vector for spreading diseases. It's everywhere and not well understood. It floats and sticks to everything but does sink eventually. The overhead exhaust would not be effective in removing the microplastics. How modeled plastic microfiber contamination in indoor spaces we see? So how do we model microplastic contamination through CFD, and if so, what were the results and how would you model it? So I think Shadab, again, you can just tell us about this question. Yeah.
Here microplastic is the source of contamination. So if microplastic is sufficient big in size and loading is also high in the domain, then in addition to that, it is also showing the characteristics of sticking. So definitely we need to model this physics by using the DPM method, that is discrete particle modeling method. And coming to the second question, that for removing the contaminants or increasing the IAQ, then definitely mixing type ventilation is not a good choice. Yeah.
Okay. Thank you, Shadab. Okay, so we have another question. So what kind of solver is used in OpenFOAM for discrete particle modeling? So the question is that is the passive scalar equation added to the solver, and is discrete particle modeling and passive scalar equation clubbed together in our OpenFOAM solver? So I think again, Shadab, you can answer this.
If you are interested in particle dynamics and want to model as a discrete particle, then there is a DPM solver available in OpenFOAM, and there are some other solvers are also available in Lagrangian folder. In our current study, we have used the species transport to model the contaminant concentration. And coming to your question again, here we are not clubbing the both species transport and DPM solver because they have their separate applicability and different objective of physics.
Okay, yeah. Thank you, Shadab. So I see that we have a few more questions regarding the solver part and the physics part of the problem. So I'll just ask them first. So the question is why steady state is used in case 2 instead of transient, and the question is again, how do you decide the turbulence model? So I think you answered about the turbulence model, but I think can you tell us an idea about why we use steady state in case 2 instead of transient?
Okay. The source of emission in the case 2 is a continuous one, and it is modeled with respect to Cow et al. Work. And we are more interested in the steady state condition here. rather than the transient behavior, which is in our first case, which is like critical application.
Okay, okay. So you are saying that these can be the, what you can say, reasons why we have chosen to go for a steady
Yes,
state,
yes.
right?
In normally office places, people more are interested in steady state conditions.
Okay, okay, sure. Thank you, Shadab. And okay, this is another question that I think you can answer. That is, what kind of mesh cells are used in far field regions? So basically, our problem. So what sort of mesh cells are used? So the question is it pure tetrahedral or is it pure hexahedral?
Okay. Um, in our meshing strategy, in mesh setup, we generally use hex-dominated hexahedral cells. And in far field regions, hexahedral will be there. And to capture the physics more accurately, we also provide sufficient number of prism layers on the surfaces of mannequin and on wall to capture the boundary layer effects.
Okay, yeah, thank you. Uh, okay, so this is another interesting question, and this is about. Can you describe more about how do we model droplets and aerosols?
Okay. Here we can here when we say droplet or aerosol, it means they are sufficiently big in size, uh, and they have the Stoke number greater than 1. It means that they can affect the momentum. So in that case, we need to model this droplets and aerosol as a separate particles, discrete particles. So we need to go for the discrete particle modeling method. In open form, there are already some solvers are there in Lagrangian folder which can address this physics.
Okay, thank you, Shada. So now we have some questions related to HVAC in general and some related to the autonomous HVAC CFD app, that one which we had shown you earlier. So I think Aditya can answer these. So one question that we have is, so we have another question here. Does this software have mesh control, and is there any limit to mesh size and number?
No, we have our mesh strategy and intelligent algorithms which can provide refinement in critical areas. And as our platform runs on a cloud, there is not as much limitation on mesh size or cell number. So you can go for any large space that you can simulate. Yeah.
Okay, so I think what Aditya is saying is that based on the geometry that you upload, the mesh size is refined, and that way. So we make sure the app makes sure that the correct mesh is generated for the given CAD model. Yeah. So thank you, Aditya. Uh, we have one more question regarding the app. So can you tell which thermal comfort parameters are currently available in the app?
So we have currently PMV, that is predictive mean vote, PPD, percentage of people dissatisfied, and also we provide draft ratings and draft rating and effective draft temperature. And we also looking for to add some IQ parameters like mean age of air and carbon dioxide concentration uh, as a tracer gas. Yeah.
Okay, so yeah, so I think these parameters, these results will be available when the app is finally ready. Okay, so we have one question about the authenticity of the results obtained from the app. So I think I can answer that. So we at Simulation Hub, whenever we create an app or whenever we develop an app, we make sure that because we develop our own CFD strategy in some way, we have certain methodology through which we perform the CFD simulation. So we make sure that we always validate it against either if there is an experimental case or there is some sort of other validation available. So we always make sure that our results are validated. And recently we have published a white paper about the validation of our CFD methodology. So if you are interested, we can share that white paper with you as well. It is available on our website, but I can share it to you personally as well. Yeah. Okay. One question we have: are external weather conditions considered in the simulation? So Aditya, I think you can answer that.
Yes, we consider external air conditions like wind velocity and solar load. Uh, as you can provide your location of your building and time for which you have to do simulation, our app takes input through the various weather stations, uh, nearest weather stations as you provide from the Google Maps. And we also consider the wall parameters like thickness of the wall and uh, conductivity. Yeah.
Okay. Thank you, Aditya. Okay, so this question is about security of the CAD model. Okay, so as you have seen that you need to upload a CAD model and then you need to provide some details when you do the simulation through the app. So definitely this question of security can arise. I'll just tell you about in brief about what are the security features that we provide. So firstly, all the data that you upload in our cloud platform, it is completely encrypted. So we use Amazon Web Services, and Amazon Web Services itself provides multiple security features which we use. Secondly, any access to your CAD data or your data is only available to our engineers when you grant us the permission. So let's say if you have a support request or you want us to interfere into a project and see what is wrong or something like that, only then the access will be granted. So we make sure that the security of your data is maintained. Yes. Okay, I think we have one last question. Is personalized ventilation the new trend for HVAC systems? So I think this question is more about because this is a new type of HVAC system that we showed. So I think Aditya, you can comment on that.
Yes, as a outbreak of SARS 2003 and MERS 2012, many researchers have suggested about that, like where people spend their most of time in office spaces or workstation. Uh, if we provide a local exhaust control, then it can reduce the contamination exposure and reduce the airborne transmission risk. So yes, in some spaces like office spaces, there is a new trend coming of a personalized ventilation system, as it mainly focuses on inhalation zone of every occupant, and each occupant can control its parameters provided as a velocity and temperatures individually. Yes.
Okay. Yeah. Thank you, Aditya. So this is it. I think those were the questions for this session, uh, and that's it from our side. And thank you everyone for attending this webinar. I hope this was knowledgeable and it provided you some interesting insights into how CFD can be used in actual HVAC design, and how we can fight this pandemic by bringing up new innovative solutions. I thank you once again for attending this webinar. And as I mentioned earlier, the recording of this webinar will be available on our website, and you'll also get a recording in your email. So thank you and have a nice day.